everyone. Welcome to Unit 3, Lesson 2. This lesson we're going to learn how to simplify radicals. First thing we're going to do is do a couple examples on converting between the mixed and entire radicals. And then we're going to look at simplifying radicals, a whole bunch of examples on simplifying radicals, and then rationalizing the denominator. One thing that I want you to remember when you're dealing with radicals is when you simplify a radical, it always has to be in simplest form. And by simplest form, we mean there are no perfect square factors. The radicand cannot have any fractions. You're not allowed to have any radical signs in the denominator, and no radicals in the denominator of any fractions. So one of the things you're going to get really good at are the perfect squares, which I'll talk about in a few minutes when I get to some of our later examples. But our first example, what we're going to go through is just a quick conversion between, let's convert from mixed to entire radicals. So convert the following to entire radicals. And what do we mean by an entire radical? That means all the numbers are inside the radical sign. These are actually quite quick to do. These are not considered to be our simplest form, but a lot of times when you're comparing numbers, it's easiest to make them in entire radical form because it's easiest to recognize which is big and which is small. So there are reasons to go to entire radicals, but they are not our simplest form. So our first example is 2 root 3. So that's a mixed radical. Remember, if there's no index given, that little subscript number on the radical sign, then you know it's to a power of 2. So the way you change to an entire radical is the coefficient out front gets raised to the index. In this case it's 2 to the 2, and multiply it by the radicand every single time. And we have a square root, so it's an index of 2 out front. Then simplify the numbers inside. 2 squared is 4 times 3 gives us the square root of 12. And a way to check is, now that you know how to punch these on your calculator, you could evaluate 2 root 3 on your calculator, evaluate root 12 on your calculator, and it should give you the same answer. Let's look at a second example. 3 cube root 5. Same process. Raise the coefficient to the index. In this case, since it's a cube root, it'll be 3 cubed times 5. Work out what 3 cubed is. Well, that's 27 times 5 should give you the cube root. Don't forget your index all the way through. Cube root of 135. And the next example, example number 3, we'll look at 2 cube root 2. Simple. Similar to the second one, but I just thought I'd give you one more practice, hammer home the point. 2 to the power 3 times 2. We're taking the cube root of it. Well, 2 cubed is 8 times 2 will give us the cube root of 16. So we're going to work with square roots and cube roots in this unit. You're going to get practice at each type. So that's how you change from mixed to entire. Example 2, let's do the reverse. Example 2, let's convert the following to mixed. It's a little bit harder process, radicals. And what it's going to have you try to remember is your perfect squares and perfect cubes. So I'm just going to write off to the side here some of our perfect squares. And what do I mean by perfect squares? Well, in your notes I was putting this. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. You should learn to memorize your perfect squares, as many as you can, ideally at least 12, and probably better yet to 15. And we also have perfect cubes. And 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. And again, you can use your calculator to help you out with some of these, but if you know a few perfect squares and perfect cubes, what you're trying to do is to factor out a perfect square or a perfect cube from your entire radical. Once you get out the perfect squares, you can write it in simpler form. So you look for the 1, the 4, the 9, the 16, or 25. These are the factors that you're trying to find to simplify. So in our first example, I'm going to give you a simple one to start. Square root 20 can be simplified. 20 has a factor of 10 and 2, but 10 and 2 isn't any perfect squares, but 4 and 5 is. So root 20 can be written as root 4 times root 5. The root of 4 is a perfect square, so we can write that as 2 root 5. And that's our mixed radical. No more perfect squares in the question. Our second one, let's go with a bigger number. Root 128. Well, you may not see this right off the start, but you could try to pull out, if what I always try to do when I get a really big number, maybe if it's even, I try to divide it by 4. If it divides by 4, then I'll see what the other number is, and then I'll try to divide by something bigger. You want to find the greatest perfect square factor, but if you find one or more than one, you just have to do the process over and over again. Yeah, I could have divided this by 4, but I also know I could divide this by 64. So this could be written as root 64 times root 2. And the square root of 64 is 8 root 2. And again, if you punch these on your calculator, you should find that when you punch in root 20, you'll get the same decimal answer as 2 root 5. And if you punch in root 128, you'll get the same decimal answer as 8 root 2. They're considered to be equivalent, just written in a simpler form. One more example using cubes. Let's take the cube root of 875, and one of the ones that I always use whenever I'm using some number ending in 5, I'm always thinking that if it's a cube, I'll try to divide it by 125. If it's a square, I'll try to divide it by 25. So 875 can be written as the cube root of 125 times the cube root of 7. Simplify, the cube root of 125 is written as 5 cube root 7. So this is considered to be simplest form. So when you're doing simplifying from here on in, we're always going to be looking to convert to mixed radicals. What I suggest, at least while you're getting used to these, if you don't know the perfect squares or you don't know the perfect cubes, write them off to the side so that you can continually refer back to them. That's what you're trying to find, factors of those perfect squares, so that you can write this in a simpler form. So there was an example on converting from mixed to entire and from converting entire to mixed. In example 2, we are doing what we call simplifying our answers. Now what we're going to do in our next examples is start to look at multiplying and dividing radicals. And again, to remind you of the rules, what we have to do is we have to simplify that there's no perfect squares. We have to make sure that there are no fractions inside the radical sign and no radicals in the denominator. Those are the 3 rules that we have to obey when simplifying. So when we start to multiply, example number 3, what we want to do is multiply 4 root 7 times 3 root 1 times root 7. So what you can do is you treat the coefficients out front separately than the radicands. If you can simplify as you go, that's great. But if not, multiply coefficients, then multiply the numbers inside the radicals sign, or the radicands. So 4 times 3 times 1 gives you 12. Root 7 times root 1 times root 7 gives you root 49. Well, the square root of 49 is a perfect square, so this gives us 12 times 7, which is 84. And again, if you were to punch that on your calculator, 4 times root 7 times 3 root 1 times root 7, you should get 84 on your calculator. Your calculator is really nice to verify these, but you will get so good at the perfect squares and simplifying that you could do it faster than you could punch it in on your calculator. Example 4. Let's do another one. Another multiplication. Let's use a cube one this time. We'll go the cube root of 32 times 2 cube root 2. Well, again, we can try and simplify this. Cube root of 32, we can see if we can simplify these. Our cube roots, again, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. So root 32, or cube root 32, can be written as cube root 8 times cube root 4. I like to simplify as I go so that I don't get such big numbers. I guess there's another thing you could do. I could do this 2 different ways for you. Actually, I'm going to do this question 2 ways for you. Method 1, we could do this the same way we did example 3. Multiply the coefficients. 2 times 1 is 2. Multiply the radicands. 32 times 2 gives me 64. And the reason why I saw that is after I was going to do it a different way, I saw that my next multiplication would actually give me a perfect cube. Sometimes it flukes out that way. Cube root of 64 is really going to be 4, so this turns out to be 2 times 4, which is equal to 8. The other way I was going to do this, and you'll notice that it won't really matter which method you choose. You could simplify first and then multiply. Cube root of 32 times 2 cube root 2 could also be simplified as cube root 8 times cube root 4 times 2 cube root 2. Well, the cube root of 8 can be written as 2. Cube root 4 times cube root 2 can really be written as times 2 times cube root 8. And you can see it's taking me a few more steps, but you'll notice that I still get to the same answer, because the cube root of 8, again, is 2, which I can simplify to getting 8. Now, the only reason why method 1 tends to be a little quicker this time is because those two multiplied to a perfect square. Had they not multiplied to a perfect square, then method 2 would be the way that you'd probably attack this. Simplify, multiply, simplify, so that you could save yourself from having to work with great big numbers. You could see if there was 3 or 4 expressions to multiply, you could get to a really big radicand, and the bigger the radicand, the harder it is to simplify. So I tend to try to simplify as I go, and sometimes it saves a little bit of work. Sometimes you could multiply. There's no real official method, all as long as that you simplify correctly and that you obey the rules. No perfect squares or perfect cubes in the radicand. No denominators that are radicals. And you got to keep simplifying until you're done. And no fractions inside. That was the other one I was thinking of. Alright, let's go to example number 5. Start to get to some harder ones. Example number 5. Let's start looking at some dividing. We have 12 root 75 over 4 root 3. Now again, there's two ways you can do this. You can simplify the top, simplify the bottom. But here's what I would do, is if the numbers go evenly into each other, reduce that, meaning the coefficients, and if the radicands go evenly into each other, you are allowed to divide those as well. So 4 can go into 12 3 times. Root 3 can go into root 75 root 25 times. Alright. So this can be really simplified as being 3 root 25, and the square root of 25 can be simplified even more as being 3 times 5, which is 15. Again, could you simplify this easier or another way? Sure, you could realize that root 75 can be really written as root 25 times root 3. Divide out the root 3's, and you're left with the same answer we have here. There's a couple ways to simplify. I always look for, do the coefficients divide into each other? Good. Do the radicands divide into each other? Good. As long as the radicands have the same index, you are allowed to do that. If you try to divide a square into a cube, then you can't do that. All right. Example 6. Let's try another one. We're going to look at 5 root 5 over 2 root 3. Notice how this question is different than example 5. It's nice to see them both on the same slide so that I could refer back to them. In this case, the coefficients don't divide in evenly. Neither do the radicands. So in this case, what we have to do is simplify. And since we have one of our rules being broken, we're not allowed to have a radical in the denominator. So the way we get rid of the radical in the denominator is we multiply top and bottom by that radical. So root 3 is in the bottom. I multiply top and bottom by root 3. The whole purpose to rationalize the denominator, is what this is called, is so that we get a whole number in our denominator. You are not allowed to have a radical in there. So whatever is in the radical sign, multiply it to top and bottom, because if you multiply it to top and bottom, you aren't really changing the number, you're just changing it form. Because root 3 over root 3 is really 1. But what we're going to do is write this in a little different form. Now simplify the top. It is 5. That's our whole number. Root 5 times root 3 will give us root 15. On the bottom, we get 2. Root 3 times root 3, well, any radical times itself will be that number. So root 3 times root 3 is root 9. Square root of 9 is 3. Or the shortcut, any radical multiplied by itself is the number inside. So this gives you 5 root 15 over 6. And you can't divide out a number from the 15 and 6. Some of you might be thinking reduce the top and bottom by 3. Coefficients go to coefficients. Radicals go to radicals. You are not allowed to divide a number out of a radical and the same number out of a coefficient. They're like x's and y's. They're not like terms. Let's look at another example. Example number 7. We're going to look at square root 48 over 150. Alright, well the first thing is you are not allowed to have fractions, so we can break this up using the property in there and write this as the square root of 48 over the square root of 150. Now I would like to try to simplify this as if possible. Well, 48 and 150, they definitely can be simplified, the radicals. 48 is 16 times 3, so I could write this as root 16 times root 3. 150 can be written as 25 times 6. So root 25 times root 6. Pulled out the perfect squares. The square root of 16 is 4 root 3. The square root of 25 is 5 root 6. Now again, I'm not allowed to have a radical in the denominator. And again, I look at this and say, root 3 will go into root 6 once root 2 times. So this could be written a little simpler as 4 over 5 root 2. If you didn't see that and you wanted to rationalize, you could have just multiplied top and bottom by root 6. But I saw that I could divide them evenly in. Just remember that when you divide evenly in, it's also times a radical. Now I'm going to write this at the bottom. I still am not fully simplified because I have a radical in the denominator. I need to rationalize. Multiply top and bottom by root 2. I end up with 4 root 2 over 5 times root 2 gives me root 4, which is 2. So 5 times 2, and again, I can simplify. Notice it really helps to try to simplify as you go to keep the numbers small and easier to work with. And that's our final answer, 2 root 2 over 5. There is a lot of different ways that you could have got this. Some people like to simplify at the end, do all their multiplying and dividing, and then simplify at the very end. Some people like to simplify as they go. It really doesn't matter as long as that you don't break any of the rules. And again, the way that you could check, punch in your calculator, square root 48 divided by 150, enter. Punch in 2 root 2 divided by 5 on your calculator, and you should get the same result both times. All right, let's do one more example. Example number 8. Lots of practice. 3 root 6 over 4 root 10. Again, there's a couple ways that you could probably simplify this. The 3 and 4 can't be simplified, but the root 6 and root 10 can be divided out. Or you could just rationalize it as is. In the last example, I simplified. Today, or this example, in example 8, I'm just going to rationalize and multiply by root 10. I just want to show you that there are lots of ways to simplify. I'm going to multiply top and bottom, in this case, by root 10 over root 10. This will leave me here with 3 times root 60 over 4. And again, any radical times itself is that number, 4 times 10. A little bit bigger numbers to work with, but that's okay. The square root of 60 has a perfect square of 4 in it. So this could be written as 3 times root 4 times root 15. 15 times 4 is 60 over 40. Simplify it one step further. Well, root 4 is 2, so this gives you 3 times 2, which is 6, root 15 over 40. Can still divide out a 2 to leave you with 3 and 20, and you end up with 3 root 15 over 20. Now the other way I would have done this is I probably would have divided out a root 2 at the beginning instead of multiplying by root 10 over root 10, and then started to simplify and rationalize after, so that I could have worked with smaller numbers. And I would have ended up with the same answer. All right. So as long as you simplify correctly, as long as you rationalize the denominator by multiplying top and bottom by the same number, you won't go wrong. Always look for those perfect squares to pull out, and then just keep multiplying. Again, if you have that list of perfect squares beside you, makes life a little bit easier to see and to look for those perfect squares a little faster. Let's go to example number 9. Here's another one that has a fraction. So we'll go with 2 root 8 over 25 times 5 root 2. Alright, well the first thing I'm going to do is simplify, because I'm not allowed to have fractions in there. So I'm going to write this as 2 root 8 over root 25. And then I'm going to go times 5 root 2. Well, the root of 25 simplifies kind of nicely. 8 times 2 gives me 16, which is also a perfect square. So I can actually simplify this pretty quick. On the top, I get 2 times 5, which gives me 10. Root 8 times root 2 gives me root 16. The bottom, square root of 25, is 5. Divide this out. 5 goes into 10 twice. Root 16 is 4, so I end up with 2 times 4. Well, that one simplified really nicely to be 8. And again, a couple different ways on how to do this. I could have just simplified root 8 to be root 2 times root 4 and then simplify it again. But again, if you can start to quickly do the multiplication in your head, and if you can find those perfect squares, whether you multiply or simplify, doesn't matter. It's when we get to addition and subtraction in the next lesson that this gets a little bit trickier. But with multiplying and dividing, you can simplify as you go very easily. And the last example we're going to do, example number 10, we'll look at 2 root 12 over 12 root 20. Alright, well, this one I'm going to already divide those coefficients. 2 will go into 12 6 times. I can also divide the radicals by root 2. So divide by root 2 will give me root 6. Divide by root 2 will give me root 10. And silly me could have divided it by root 2 again. So divide by root 2 gives you root 3. Divide by root 2 gives you root 5. No matter what you do, as long as you do it to top and bottom, you are not changing the expression. So this thing simplifies to be root 3 over 6 root 5. There's no more numbers to divide evenly into top or bottom. So now I'm going to rationalize. I'm not allowed a radical in the denominator. So I'll multiply top and bottom by root 5. So I get root 3 times root 5 to give me root 15. On the bottom, I get 6 times 5, which is 30. So I get root 15 over 30 as my final answer. And you could punch this in on your calculator to verify. So simplify the coefficients. 2 into 12 goes 6 times. I looked at dividing out root 2 from the top, root 2 from the bottom. So 12 divided by root 2 is root 6. 20 divided by root 2 is root 10. Saw that I could do it again. Root 6 divided by root 2 is root 3. 10 divided by root 2 is root 5. And then simplify. Root 3 over 6 root 5. Rationalize. Root 15 over 6 times 5, which is 30. That's lesson 2. Get lots of practice in exercise 2 on converting from mixed to entire, and then a whole bunch of practice on simplifying. And again, when you check the answers, there may be more than one way to do these, but as long as you don't break the rules, whatever you multiply or divide to the top or bottom has to be the same number. And when you rationalize, you multiply top and bottom by the same number. Take care, everyone.